In this video here, we're going to take a look at pulleys. We're now going to build on what we've learned in the previous video to look at how we can model systems of connected particles involving pulleys. And the questions that you answer in this video and chapter will assume that particles are connected by a light inextensible string and that they pass over a smooth pulley. Now, as a result, what this means then is that the tension in the string will be the same on both sides of the pulley. And a common mistake here then with pulleys is to treat a system as a single particle. But we can't do that. And the reason for that is because the particles will be moving in different directions. So in terms of an introduction here to pulleys, we don't need much more than that. So really, I think the best way to demonstrate the concept of pulleys is just work through a practice question together. So let's just have a go then at this one practice question here. So for this question, we have a box P of mass 2 kilograms that rests on a rough horizontal table and is attached to one end of a light inextensible string. We're told that the string passes over a smooth pulley fixed at the edge of the table, and the other end of the string is attached to a ball Q of mass 3 kilograms which hangs freely below the pulley as shown in this diagram here. We're then told that the magnitude of the frictional force between the table and the particle P is K newtons. The system is released from rest with the string taut, and after release Q descends 0.4 meters in 0.8 seconds. So the question then says by modeling P and Q as particles, find, and then we want to find a few different things here. So let's begin then with part A. So for part A then, it wants us to find the acceleration of Q. So before we jump into part A, let's just quickly add the relevant forces here to our diagram. Okay, so we're already given the diagram. We don't need to draw anything other than the relevant forces. Okay, so to begin with here, the particle P has a mass of 2 kilograms. So the weight then is 2g, acting vertically downwards here. So that's 2g. And we also have a normal reaction here as well. Okay, so we have a normal reaction here. Let's just label that as R, like so. We've got tension in the string here. I've got tension in the string. And same again here. So we've got tension here as well, like so. And we've also got the weight here of the particle Q. So Q has a mass of 3 kilograms. So the weight then is 3g. Okay. We've got the acceleration. So in this case here, it's going to accelerate like so. And this will accelerate vertically downwards. That's for the particle Q, like so. And then finally, the only thing that we're missing here is the frictional force. Okay, so that's the frictional force then between the table and the particle P, which in this case here, as we're told, right, is K newtons. That's just K there. Okay. So there we have it then. That gives the relevant force diagram here to answer part A, part B, and part C. So for the first part of this question, then part A, as we've just mentioned, right, we want to find the acceleration of Q. So to find the acceleration of Q, all we need to do here is use the trusty old Suvat equations. So using Suvat here, let's just make a note. Using Suvat here, what do we know then? So this is for the particle Q here. So for Q, what we know then is S here, the displacement, is equal to 0.4. So S is equal to 0.4 there. That's our displacement. U, the initial velocity here is 0 because both of these particles start at rest. So U is 0. We don't know what A is. That's what we want to find, right? So we'll put a question mark there because that's what we're looking to solve for. And then finally, we also know T here. So T is equal to 0.8. Okay. So based on what we've got here, then we're going to use the following Suvat equations. So we're going to use them. So we're going to use S equals UT plus a half AT squared. Okay. So S then is 0.4. So 0.4 is equal to ut, so that's 0 times by 0.8, which clearly is just 0 anyway, but I'll write it down just so you can see the full working. So 0 times 0.8 plus a half, so a half or 0.5, whichever you prefer, times a, which we don't know, right? So a half a there. And then we times this by t squared, so 0.8 squared, like so. So I've got 0.4 here is equal to, so 0.8 squared would give me 0.64. We then times it by a half. So what I've got here then is 0.32a, so 0.32a there. Well, clearly then, if we just want a here, all we need to do, right, is just divide both sides by 0.32. So in that case then, a here, the acceleration of q, is equal to 0.4 divided by 0.32. And this gives us here then 1.25. So we get 1.25 meters per second squared there because we're talking about the acceleration, right? And there we have it. So the acceleration of q here, so the acceleration of q, the acceleration of q is 1.25 meters per second squared there. Okay. And there we have it. So that gives us the solution to part A. So now for the second part of this question here then, part B, we now want to find the tension in the string. So again, we consider the particle Q here. So for Q here then, what we're going to do now is resolve vertically here. Okay. I'm going to take downwards as positive, given that it's accelerating vertically downwards here. And we also need to use F equals ma as well, because the system is accelerating. So in that case then, as we've just mentioned, right, we're resolving vertically here, taking downwards as positive. Okay. So what do we have here then? Well, forces acting downwards, we have 3g. So I've got 3g. So 3g. There's no more forces acting downwards, so we now consider what forces are acting in the opposite direction. So in this case, acting upwards, which in this case is t here. We get 3g minus t is equal to the mass times the acceleration. The mass here is 3, and then we times it by the acceleration, which in this case, as we've just deduced in part A, is 1.25. Okay, so 3 times 1.25 there. Okay. Well, in that case then, t here is equal to 3g minus 3 times 1.25. So t is equal to 3g minus 3 times 1.25. So all you need to do here then is just use a calculator, right, to evaluate this here. I'm rounding our answer to 2SF here, so 2 significant figures. What we get then is 25 newtons here. Okay. So there we have it. That gives us the solution to part B. So the tension in the string then is 25 newtons. And then finally here, for the very last part of this question, part C, we want to find the value of K. So don't forget then, K here is the magnitude of the frictional force between the table and the particle P. Okay. So let's do that over here. So for part C, what we now need to consider here is the particle P. So for P then, what we're going to do here is resolve horizontally. So resolve horizontally here then, taking to the right as positive. Okay. And again, what we're going to do here is use F equals ma. Okay. So forces acting to the right then, that is T. So we have T here, the tension, which obviously we've just deduced in part B, but I'll leave it as T for now. Forces acting to the left then, in the opposite direction, that's just K. So we get T minus K is equal to the mass times the acceleration. So the mass here is 2, times that by the acceleration A. Okay, so we get T minus K is equal to 2A. Well, we want the value of K, right? So in that case then, rearrange here, making K the subject. what we get here then is k is equal to t minus 2a. Okay, well, we know t, we figured that out in part B. We know a, we deduce that in part A. So let's just put all that together then. So k here is equal to t, which is 25, minus 2 lots of a, so minus 2 times 1.25 here. So basically what we've got here then is 25 minus 2.5. In that case then, the value of k here, so k is equal to 22.5 newtons there. Okay, and there we have it then. So that gives the solution to part C. This was the solution here to part B, and this was the solution here to part A. And there we have it. So that gives the solution to this question here. And that actually brings us to the end then of this video here on pulleys.